Hello class, welcome to my first video lecture. I hope everything is going okay for you. I hope this video finds you well. Please stay cautious, stay inside, please follow the orders, but we are trying to get back into the swing of things. So I am going to start our first lesson dealing with exponential functions. Where we left off, I know we were supposed to have a quiz the day we were supposed to come back, that Monday before the end of the marking period. For right now, that quiz is on hold. I may give it to us if we come back for fourth marking period. I may just scrap that quiz. I will let you guys know as decisions are being made and seeing what is happening. But for right now, I'm going to move forward with Chapter 3. Chapter 3 starts with exponential functions and their graphs. So if you have a textbook at home because you borrowed one, this is section 3.1. I will post a PDF of the notes I gave last semester on this, and you may see me looking down over here at the textbook or at my laptop as I have our notes up. So some important vocabulary for this is the first definition they give us is transcendental functions. These are functions that are a little different than the normal like polynomial and rational functions we've seen. Basically, it follows the idea of exponential functions. So both exponential and logarithmic, which we'll get into in a little bit. Right now we're just focusing on exponential, fall into this category of transcendental functions. Now the natural base e, we are learning a new number. E is a rather special number. It is a rational, it is not a rational number. It's an irrational number, very similar to pi. And just like the number pi, this appears a lot in nature. So a lot of things can converge, and patterns with exponentials oftentimes will start to converge to the number e. E is defined as, E is approximately 2.71828. Now, if you are using, I probably want to write that bigger for you guys. Sorry about that. Let me write that nice and big. E is approximately 2.71828. Now, if you are using a calculator at home, I know I've told you guys about getting used to that Desmos calculator. If you type the letter E in Desmos, Desmos has assigned it to be like, oh no, E is not a variable, E is a number. If I open Desmos, which I have here, and I just go to this and type in the letter ABC. If I type in the letter E, let me make sure it is easy to read from there. You will see the letter E. All I do is type in the letter, and it gives me the decimal approximation. So E is approximately 2.1782. It keeps going a little further in Desmos, but you get the idea. So that gets our vocabulary out of the way. So now, polynomial functions and rational functions are what we call algebraic functions. That's what we've studied a lot so far in this course. And like I said, now we're moving on to exponential functions. An exponential function with a base of a is denoted by f of x is equal to a to the x. Notice how the variable is up here in the exponent. Since the variable is up there in the exponent, that's what makes it an exponential function, whereas a polynomial would maybe look something like f of x is equal to x squared minus 2x. Notice the x's are down here, not up in the exponents. Hence the difference between a polynomial and exponential function. Exponential, we want to see that variable in the exponent. Now we will say that the a value here will have to be greater than 0. Because when we start taking powers of negative numbers, things can get a little weird. So we never want to make this a value negative. We always keep it positive. And we'll never want this to be 1, simply because of the fact that 1 to any power is just 1. That's a rather boring function, which will just be a straight line. So, what we're going to do for our first example is we are going to see how we can use the calculator. I'm using the standard Desmos graphing calculator that I've been encouraging you guys to use all semester, and show how it can evaluate something. So example 1 just says to do 5 to the 3/5. Now when I have a fractional exponent, this denominator down here actually tells me that I want the 5th root of this. This can be rewritten as the 5th root of 5 cubed. Now, what we're going to do is we're going to, again, utilize Desmos here. We're going to utilize the calculator to evaluate this. Finding the 5th root of 5, that's not something you're going to know off the top of your head. Then cubing that number is going to be rather difficult. So what we are going to do is just utilize our calculator. So inside of here, I am just going to say 5, and then I will go this exponent AB. Since it is a fractional exponent, I'm just going to do 3 divided by, whoop, that says 6. Let me delete that. Delete, there we go. 3, then fraction 5. And all I did was simply type it in, and it gives me my numerical value over there. Again, a lot of these are going to turn out to be irrational numbers, so we are just going to round them off. I'm going to give the recommendation, give me 4 decimal places. 4 decimal places, please. So this is approximately, added an extra 0 in there, there we go. So according to this, it is approximately 2.6265. And that is it. So in the homework or classwork that I'm going to assign, the work that I'm hoping you are doing to engage with this, this will align with the first group of problems that I assign. All we're doing is putting it in. So if it, whatever it tells you to put in for X, just put it in for X in the calculator and let the calculator do all the hard work. You're just typing it in because these are not pretty to calculate by hand. In fact, to calculate by hand, you'll probably need to use tables and all that. And with modern technology of calculators, there's no sense looking things up in a table like that. So, for these functions, if A is greater than 1, we're always going to look at these not to be fractions. We're always going to try and use a whole number for A, and then use the exponent to tell if it is increasing or decreasing. So, here with this, assuming A is greater than 1, if I have f of x is equal to A to the positive x, this is an increasing function. So this will look something like so. It grows at an exponential rate. And that growing at an exponential rate, things start moving very, very fast as we start even putting in modestly big numbers for that. And that's to bring this into the real world context of what's going on today. We have an exponential increasing function with the virus growth. And that's what the worry is. If we can slow that growth even by a little bit, it helps keep the numbers down. Hence some of these precautions we are taking. Now the modeling section is section 5 in the textbook. I will talk about some of those ideas, but we don't fully need to cover it. So in section 5, if you're more curious about how these models are made, looking at exponential functions, please let me know and I can include like a discussion on it, but it's not a topic I'm formally going to be covering. Anyways, my big point here though is since this exponent is positive, is an increasing function like this. If I make the exponent negative, so if I say a again is greater than 1 and f of x is equal to a to the negative x, this is a decreasing function. So eventually we're hoping there are ways to get the increasing and decreasing curves to combine by putting like x squareds and things like that as the exponent to it. But we're hoping to eventually have it meet up, this graph turn around into this exponentially decreasing graph where hopefully the virus will flatten that curve and will start to go away and hopefully bring life a little back to normal. So, as far as the domain for these graphs for both of them, the domain is all real numbers. Now the range is a little more unique. If we notice, it appears in my drawings, and if I bring up a quick example on Desmos, let me just get this. Let's do 5 to the x. And if we look at Desmos as well, we can see it appears that it never crosses the x-axis. So it appears I have an asymptote with the x-axis, but it definitely keeps going up forever at a very rapid rate. So the domain is all real numbers, while the range is y is greater than 0, as that is the default asymptote. And for all of these, if we plug in 0 for x, anything to the 0 power is always 1. We will get a y-intercept of 0, 1. So when we are graphing these, I do expect to see good asymptotes using this. Now, if I add 5 to the function, it will shift it up 5 units. If I subtract, it will move it down 5 units. And also having a initial default y-intercept at 0, 1. Now that could be changed. If I said 5 times our exponential function, that would be changed to 5. Or if I shifted something left or right, this point would just get moved left to right. We've done a lot of function shifting. I'm not asking you to do that for the work that is assigned with this section, but we've seen those ideas. So let's see. Our second example, and this is dealing with the next group of problems we do deals with sketching the graph of 3 to the negative x. So we're going to find some important information here and go from there. Then we'll again compare my graph to the graphing calculator. So example 2, graph f of x equals 3 to the negative x. Now the larger this number is, again, the faster that growth will be. But we're just doing a nice rough sketch here. 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, so right away, I know this is a decreasing function because of this negative in here. So decreasing comes from the negative. Now my y-intercept, since I am doing nothing else to the function, will default to 0, 1. So let's place that point here. And of course I will have an asymptote, a horizontal asymptote, still using the same abbreviations we used in the previous chapter. HA for horizontal asymptote will default to y equals 0. So with y equals 0, remember, that means I'm never crossing the x-axis. So I want to draw a nice, smooth, decreasing curve through this point, but never cross here. So that will look something like so. So again, when I'm looking at our sketches, I'm looking for a faster turn up this way and a very slow descent here, or if it's an increasing function going right along here, then rapidly picking up as we approach the y-intercept. So that is the sketch of our graph. Please remember, just like I said with rational functions, I do not expect to see you get lazy and have these lines cross your asymptote. I also don't want to see them well above your asymptote as well. When we have an asymptote, it approaches it but never crosses it. So I really expect to, as I've used in the past chapter, it to ride that asymptote. Now there is no vertical asymptote on these functions because there's no division by 0 happening here. So the next thing we are going to talk about is, again, that natural log function. So, or natural log function, we'll talk about that later. We'll talk about the natural exponent e. So the natural exponential function is just e to the x. So by default, it is increasing since it's e to the positive x. And again, for example 3 here, we're just going to look at plugging in e to the 3/5 into our calculator. So we're going to see a lot of repeated information here. But again, let's look at putting that into the calculator. Now, like I had said, Desmos, and I can't think of a calculator program that wouldn't do this. E is not assigned to be a variable. E is assigned to be this number, was at 2 point, I just said it earlier. Where is it in the textbook? 2.71828, so forth. So all I'm going to do is go to my keyboard, type the letter E. It's already giving me that. So then I go exponent, and it says 3/5 again. So I'm going to type in 3 divided by 5. 3 divided by 5. And there we go. All I did was type it straight into the calculator, and it gives me my answer. So, in doing this, I get this is approximately 1.8221. Again, I'm asking you to give me 4 decimal places. So for the function e to the x, the domain and range and y-intercepts are no different than any other exponential function. Our domain will still be all real numbers. Our range will be y is greater than 0. And our y-intercept will be 0, 1, because e, like any other number to the 0 power, is still defined as 1. So, the number e can also be approximated through, e is approximately 1 plus 1 over x to the x for large values of x. So what this is saying, this leads us to some interesting conclusions that we're just, for this course, take them to be what they are now. When you explore things further in calculus, you'll get more of an explanation of what's really happening here. But as I start to put bigger and bigger numbers in here, we get very close to the value of e. So again, I'm going to speak a little bit of calculus quickly. The limit as x approaches infinity on this is e. So that will allow us to create special equations for continuous interest. So that takes us to the final and last part of our notes with applications. So you guys probably remember from previous courses talking about simple and compound interest and how that happens in banks. So, let me give you the formula for those. For continuous interest, our amount, this is for, sorry, not continuous, for compounding interest. I want to give you that equation first. A is equal to our principal, P, times 1 plus our yearly interest rate, R, over the number of times it's compounded to the T, how many years it's been, times the number of times it's compounded. So if I compound 12 times a year, that's once a month. I'm going to have to divide that interest rate by 12 because it makes sense. I only earn a 12th of the interest through 12th of the year. So that makes that 1/12. So that means it's happening if it's 1 year, 12 times that year, hence the T times N. So that's our compounding interest formula. This you've seen in previous classes. Continuously compounding interest, so works a little bit differently. If you notice, this 1 plus R over N to the T times N. Well, if you notice, this looks a lot like the formatting on what I just showed you approximately goes to E. So as this formula, as N becomes larger and larger and larger, it converges to E. So for continuous compound interest, we get a new formula. Based off of the number E. Per amount equals principal times E to the R times T. where R is the annual interest rate and T is the amount of time. So we got one final example to do before I gotta say, hey, look on Schoology, see what problems I have assigned for you to try. Use the guided notes to help you, and use this video to help you as well. So we're going to look at the difference between compounding monthly on some money for 10 years versus compounding continuously. And we are going to see that one makes us more money than the other. So, example 4. Says, find the amount in an account after 10 years with an initial investment of $6,000 at an interest rate of 7%. So let's see what happens here. For part A, it asks us to do it for compounded monthly. So for A, the other red marker seems to be writing brighter for you guys. It's saying compound monthly. So that's going to be N is equal to 12. Now for part B, it's going to say continuous. So for continuous, I do not have to worry about an N value. I just need to know the principal, rate, and time. And E, hey, we're just going to utilize the calculator for it. So continuous. So part A asks me, there we go, that's brighter red marker, to plug in. So my principal investment. So for part A, our amount's going to be equal to my initial investment of $6,000. That's P. That's the principal amount. So I'm investing $6,000. Then it says 1 plus. Now my yearly interest rate is 7%. Remember, we need to write percentages when we're using them inside of an equation as decimals. So that means move it to the left twice. So that's going to be 0.07 over, since it's compounded monthly, my N value is 12. Now my exponent will be T, my time, times my N, 12. So 10 years it's invested with being compounded 12 times every year. So what it's saying is, hey, you're going to earn your interest 120 times. This is now just a matter of very carefully and deliberately putting this into the calculator. So let's take a look at what happens when we do that. So please make sure when you type it into Desmos, it looks like how we wrote it down. And I would expect to not just see the answer. I want to see what you're typing in. I know the calculator's doing a lot of the heavy lifting here. I want to know what's going into the calculator, so I know you're just not randomly copying it. I know, hey, I took the time, I put this in the calculator, this is what I got. So let's do that. 6,000. Now I have parentheses. 1 plus. Now I have a fraction there, so that's 0.07 divided by, notice, it's giving me a little error there just because I didn't put anything there. But notice how it's just this little piece here that's the fraction. The 1 is not involved with this fraction over 12. I'm going to hit over. I want to close. I want to close this big set of parentheses so I can get my exponent. So again, I'm going to hit the A to the B button, and I'm just going to type it in. 10 times 12. Well, it looks like when I hit times, it moved it out of that exponent, so I want to make sure I'm back up there. Okay, it's not liking that, so what that's telling me is I probably want to put parentheses around that, or you could have just done 10 times 12 and put it as 120, but I'm just going to type it in just how I did. So I put parentheses around that whole exponent, and I get that my investment of $6,000 will turn into $12,057.97 in a matter of 10 years. So not bad. Made more than twice as much money as what was in there. Now, a 7% interest rate, getting that, I mean, that'd be awesome. Unfortunately, a lot of places aren't offering as high as 7% interest, but 7% interest is really going to help highlight the difference between compound interest versus continuously compounding interest. So now for part B, we are going to do the same thing. My principal is still $6,000. Now I'm going to say times E to the 10, interest rate first, to the 0.07 times 10. So like we just found on the previous problem, I'm probably going to want to put parentheses around this whole thing. Now, you're quick with your multiplying, you could realize that just E to the 0.7, and you could type it in that way. But if you want to have the fail-safe, make sure you didn't do any of your mental math wrong, you can type that in as is. So $6,000 times, now again, just type in the letter E. It's already doing what I want. Now to the power, it says 0. Oh, I want to put parentheses. I just talked about that. There's my parenthesis. 0. Nope, not 1. 0.07 times 10. And there we go. What we see here is I get $12,082.52. So it's not a massive difference between the 2 years, but I'm sure most people won't be complaining about what's almost an extra $25. Now, when we're talking about, well, I had that $6,000 to begin with, it seems like small change, but hey, $25 is still $25. So we get $12,082.52 after we round it up. So this is all we're looking to do right now with exponential functions. So your work being assigned, and I will make sure these pages are uploaded to Schoology, is pages 189 to 190. You're going to do 6 through 16 even. That deals with examples 1 and 2. You will do 40 through 46 even. Those are all dealing with the idea of E being a little more involved. So again, you can look at example 2 for some help there with sketching those graphs. And then finally, 58 looks at this application of interest. Now, I'm only asking you to do one problem there because it does ask you to do compounding interest for compounding once a year, twice a year, 4 times a year, 12 times a year, 365 times per year, and then continuously. So you'll get to actually see the difference as we start compounding our interest more often, how it makes that money grow faster and grow by more. So I hope this video lecture finds you all well. I'm signing off for now. Have a good day. If you have questions, I am reachable through Schoology and through my school email. So please send those questions my way, and have a great day.